Hello. Today, we're going to dive into the fascinating world of trigonometry and polar coordinates, which is topic 3.13 in AP Precalculus. By the end of this lesson, you will be able to determine the location of any point in a plane using both rectangular or Cartesian coordinates and polar coordinates. To achieve this objective, we'll cover a few essential topics. First, we'll establish a solid understanding of the polar coordinate system itself. Second, we'll learn the formulas for converting from polar coordinates to rectangular coordinates. Third, we'll work through the process of converting from rectangular coordinates to polar coordinates. And finally, we'll see how these concepts can be used to represent complex numbers. Let's begin by contrasting the two primary ways to describe a point in a plane. Most likely, you're already very familiar with one of them. We have the rectangular coordinate system, also known as the Cartesian system, and the polar coordinate system. Both are just different ways to map out a plane. In the rectangular system, a point's location is defined by its horizontal and vertical distances from the origin. We use an ordered pair, x, y. The x-coordinate tells you how far left or right to move from the origin, and the y-coordinate tells you how far up or down. Now, let's explore the polar system. It describes the exact same plane but uses a different set of rules. Instead of an x and y, we use r and theta. The ordered pair is r, theta, and they represent a distance and an angle. This system is based on a grid of circles centered at the origin, and lines that pass through the origin at various angles. Notice how different this grid looks compared to the rectangular one. Both systems, however, are just frameworks for pinpointing a spot. So, what are these r and theta values? R stands for the radius, or the directed distance from the origin to the point. This distance r is determined by the specific circle on which the point lies. Theta is the measure of an angle in standard position whose terminal ray includes the point. This angle theta is determined by the specific line through the origin that the point falls on. So, let's recap. Both systems have an origin and an axis. In Cartesian, we have the x and y axes. In polar, we have the pole, which is the origin, and the polar axis, which is the positive x-axis. A point is xy in one system and r theta in the other. It's important to know that in the polar system, a single point can have infinitely many representations. A point with coordinates, r theta, is the same as a point with coordinates, r theta plus 2n pi, for any integer n. For example, the coordinates 2 pi over 4, 2, 9 pi over 4, and 2 minus 7 pi over 4 all refer to the exact same point. This happens because adding or subtracting 2 pi to the angle just brings you back to the same terminal ray. So, a point is defined by its distance r and its angle theta. The coordinates, 2, pi over 4, indicate the point that is 2 units away from the pole along the ray for the angle pi over 4. But 2, 9 pi over 4, and 2 minus 7 pi over 4 describe the very same location. What if r is negative? A negative value for r means you should go in the direction opposite to where the angle theta points. For example, to plot minus 3 pi over 6, you'd find the terminal ray for pi over 6, then go 3 units in the reverse direction. This is the same point as 7 pi over 6. A negative r value effectively adds or subtracts pi from the angle, flipping the ray to the other side of the pole. We can represent any point in both systems. But what if we're given coordinates in one system and need to find them in the other? That's where conversion formulas come in. First, let's learn how to convert from polar coordinates r theta to rectangular coordinates xy. Let's visualize a point P at xy in the Cartesian plane. We can draw a line from the origin to P. This line has a length r and makes an angle theta with the positive x-axis. If we drop a perpendicular line from P to the x-axis, we form a right triangle. In this right triangle, the x-coordinate is the adjacent side to the angle theta, and the y-coordinate is the opposite side. The hypotenuse is r. Using our basic trigonometric definitions, we know that cosine theta equals the adjacent side over the hypotenuse, which is x over r, and sine theta equals the opposite side over the hypotenuse, or y over r. Rearranging these equations gives us our conversion formulas. So, our two key formulas are x equals r times cosine of theta, and y equals r times sine of theta. These allow us to find the x and y coordinates of any point if we know its r and theta values. Let's work through an example of this conversion. Suppose we are given the polar coordinates 2, pi 3, and we want to find their rectangular equivalents. Here, r is 2 and theta is pi over 3. Our goal is to find x and y. First, let's find x. We use the formula x equals r cos theta. Plugging in our values, we get x equals 2 times cos pi 3. Remember from the unit circle that the cosine of pi over 3 is 1/2. So, x equals 2 times 1/2, which simplifies to 1. The x-coordinate is 1. Next, let's find y. We use the formula y equals r sine theta. Plugging in our values, we get y equals 2 times sine pi 3. The sine of pi over 3 is the square root of 3 over 2. So, y equals 2 times the square root of 3 over 2. The 2's cancel out, leaving us with y equals the square root of 3. The y-coordinate is the square root of 3. Therefore, the rectangular coordinates that correspond to the polar point, 2, pi 3, are 1, square root of 3. So we have successfully converted from polar to rectangular coordinates, using our formulas. Now, let's go the other way. What if we are given rectangular coordinates, x, y, and need to find the polar coordinates, r, theta? We'll be converting from rectangular to polar. Let's return to our right triangle. By the Pythagorean theorem, the square of the hypotenuse is the sum of the squares of the other two sides. In our case, this means r squared equals x squared plus y squared. Taking the square root of both sides, we get our formula for r. The absolute value of r is the square root of x squared plus y squared. This gives us the magnitude of r. If the angle theta places the point in the correct quadrant, we can choose the positive r value. If we use an angle that points to the opposite quadrant, we can use a negative r value. The convention is often to find the primary angle theta first, and then determine if r should be positive or negative based on the location of the point. To find theta, we can use the tangent function. The tangent of theta is the opposite side over the adjacent side, which is yx. So, we can find theta by calculating the arctan of yx. This formula, however, comes with a crucial caveat. The standard range for arctan is only from negative pi over 2 to positive pi over 2, which only covers quadrants I and IV. This means we'll need to do some extra work to find theta if our point is in quadrant 2 or quadrant 3. So, how do we handle those cases? We need a more comprehensive rule for theta. The key is to first determine the quadrant where the point xy lies. If the point is in quadrant I, both x and y are positive. The angle theta will be the standard arctangent result. If the point is in quadrant 2, x is negative and y is positive. Here, theta is pi plus the arctan of yx. You're adding pi because the arctan result would be in Q4, and you need to flip it over to Q2. If the point is in quadrant 3, both x and y are negative. Again, you add pi to the arctan result. The arctan of two negatives is in Q1, and adding pi puts it in Q3. Finally, if the point is in quadrant IV, x is positive and y is negative. In this case, theta is either 2 pi plus the arctan result to keep it positive, or simply the arctan result itself. Both are valid. A good practice is to always plot the point first, to visualize the quadrant, and then use the correct formula. Let's apply these rules with an example. Let's convert the rectangular point -1, -1 to polar coordinates. Our values are x equals -1 and y equals -1. The first step is to plot the point. Both coordinates are negative, so the point lies in quadrant 3. Knowing it's in Q3 is critical for finding the correct angle. First, let's find r. We use the formula r squared equals x squared plus y squared. Plugging in our values, we get r squared equals -1 squared plus -1 squared, which is 1 plus 1, or 2. So r equals the square root of 2. We'll choose the positive value for r. Now for theta. Since the point is in quadrant 3, we use the formula theta equals pi plus arctan yx. Plugging in our values, we get theta equals pi plus arctan, -1 -1. This simplifies to pi plus arctan 1. We know that arctan 1 is pi 4. So theta equals pi plus pi 4, which gives us 5 pi slash 4. So the polar coordinates for the point, -1 -1, are square root of 2, 5 pi slash 4. Notice how important it was to identify the quadrant to get the correct angle of 5 pi slash 4, not just pi 4. There are a few special cases we should address when converting to polar coordinates. The arctan, yx formula, doesn't work if x is 0. The point is on the y-axis, If x equals 0 and y is greater than 0, the point is on the positive y-axis. The angle is pi 2. Similarly, if x equals 0 and y is less than 0, the point is on the negative y-axis. The angle is 3 pi/2. The other special case is the origin itself. At the origin, x and y are both 0. If we try to use our formulas, we get r equals 0. But for theta, we have a problem. The arctan of 0/0 is undefined. This makes sense. A point at the origin doesn't have a specific angle, so its polar coordinates are 0 theta, where theta can be any angle. We'll simply write 0, 0 as a standard convention. These cases highlight why plotting the point first is always a good strategy. Let's finish our lesson by seeing a powerful application of these coordinates in a different area of mathematics: complex numbers. You may have encountered complex numbers in the form a plus bi, called the rectangular form. We can visualize complex numbers as points in the complex plane. The real part, a, is plotted on the horizontal axis, and the imaginary part, b, is plotted on the vertical axis. So, the complex number a plus bi corresponds directly to the rectangular coordinate point AB. Since any rectangular point can be converted to polar, any complex number can also be written in polar form. Here, r is called the modulus, which is the distance from the origin to the point AB. It's calculated as the square root of a squared plus b squared. The angle theta is called the argument, and it's calculated using the same rules we just discussed, the quadrant-adjusted arctan of b over a. So, our conversion formulas for x and y become conversion formulas for a and b in the complex plane. The rectangular coordinates a and b correspond to the real part x and the imaginary part y. Thus, we have a equals r cos theta and b equals r sine theta. Substituting these back into the rectangular form a plus bi gives us this expression. This is one way to write a complex number in polar form. We can factor out the r. This gives us the modulus r multiplied by the quantity cosine theta plus I sine theta. This is the more common and useful polar form for complex numbers. Let's quickly convert the complex number -1 plus I to polar form. Here, a equals -1 and b equals 1. First, we find the modulus. R equals the square root of -1 squared plus 1 squared, which is the square root of 2. Next, we find the argument. The point, -1, 1, is in quadrant 2, so we use the formula theta equals pi plus arctan BA. This gives us pi plus arctan 1/1, or pi plus arctan -1. Since arctan minus 1 is negative pi 4, we get theta equals pi minus pi 4, which is 3 pi/4. So, the polar form of the complex number, -1 plus I, is the square root of 2 times cosine of 3 pi/4 plus I sine of 3 pi/4. This polar form is incredibly useful for multiplying and dividing complex numbers. Today, we have explored the polar coordinate system, learned how to convert between polar and rectangular coordinates, and saw how these concepts extend to representing complex numbers. We have successfully met our objective of determining a point's location using both rectangular and polar coordinates. Great work!